Okay, dear students, now comes question 11, and here you are asked to find the value of k for which this particular matrix can be singular. So I'm going to show you how this can be obtained. Not only this, basically, there is also another additional question here. You see, Roman number 2. You are given here 3 by 3 square matrix, and again k is introduced, so you are expected again to find the value of k for which this can be non-singular. So students, first, before you calculate or before you dive into finding the solution, you have to understand what we mean by saying singular and non-singular matrices. Students, if the determinant of a square matrix comes 0, then the matrix is not invertible. And in the case of this, we call it a singular matrix. And whereas if you take the determinant of a certain square matrix, and if non-zero value comes, then the matrix is said to be invertible. That is to say, we are able to find the inverse of the given matrix. So this sort of matrix is called a non-singular matrix. So what we need to do in order to find the values of k above for the two matrices is we just apply determinant, and for the first case we will try to look for k where the determinant can be 0, and for the second case we'll try to find the value of k for which the second matrix determinant comes to be non-zero. So here I start from the first one. Look, the matrix entries are k minus 2 and minus 1, k minus 1, as you see. So we need to find the determinant. As we stated before, the determinant of a 2 by 2 size matrix is nothing but it is a product of the diagonal entries. As you see, the product of the diagonal entries minus the product of the non-diagonal entries, as you see. So k times k minus 1 comes, and then minus comes here. The product of these two is 2, because negative 2 times minus 1 is negative 2, as you see. So when you operate this, k times k comes to be k squared, and here we have k minus 1 minus 2, as you see. Now let's factorize this. As you see, try to think of two numbers where their sum can be negative 1 and the product negative 2. Those numbers are minus 2 and 1, so you can have these two products, k minus 2 and k plus 1, as product of, you see, these two, this expression. So k minus 2 times k plus 1 can make k squared minus k minus 2. Since we are looking for the case where the matrix is singular, you see we need to observe the case where the determinant is going to be 0. So for this matrix not to be invertible, we must look for values that can make the determinant 0. So as you know, this determinant is the one we obtained above. K minus 2 times k plus 1 gets 0 when k is either 2 or k is 1, because the product of these two, as you see, comes 0 if either k minus 2 or k is minus 1, okay? Either k has to be 2 or k has to be minus 1. So have here minus 1, students. Just have that correction here, or let me just correct that right now. So as can be shown, either k needs to be 2 or k needs to be minus 1, because k minus 2 gets 0 when k is 2 and k plus 1 gets 0 when k is minus 1, okay? Now proceeding to the second case, that is a case where the matrix, the next matrix, is non-singular. So in the case of this, the determinant should be different from 0, as I said earlier. So we have to look for the determinant of this 3 by 3 matrix. As you see, the entries are here. So students, as a tip, I would like to recommend you to select a row or a column having 0, because selecting that radius performing one term simplification, okay? So here we have 0 in the first column and in the second row, as you see. In the first column we are having 0, and in the second column also we are having 0, and the second row, I mean, we are having 0. So you can expand this by using either first column or second row, right? Because 0 is 0. So now this already has been done by using second row expansion. Look, this is a second row expansion. So if this is assigned to be plus, students, then this is going to be negative, and for 1 we do have a positive. So take number 1, as you see, 1 is taken here, it's understood that it's not written, though it's not written, there is 1 here. So try to delete, you see, the row where 1 is obtained, and also the column again 1 is obtained. So try to delete that. So the second row and the second column should be deleted. So as you delete these entries, you are left with 2, 3, minus 2, minus 3. You see, students, 2, 3, and minus 2, and minus 3. So you are going to face this determinant. Now, since I'm looking for the determinant using secondary expansion, I can also now consider this to be negative k. Mind you that if you assign plus here, this is going to be negative, and this is positive, and this is negative. That's why I'm taking negative k here, you see? Because k is obtained at the intersection of second row and third column. Second and third. So we have 2 and 3 because of second and third. So this entry is basically a to 3. a to 3. So 2 plus 3 makes 5. And we know that minus 1, the power of 5 is negative. And because of this sake, we are having here minus k. Okay? So minus k is taken. So negative k is taken. Now we need to delete the row with, you see, the second row and the third column, because this k is obtained or located at the intersection of second row and third column. So as you are doing that, you are left with entries like 2, minus 1, minus 2, minus 1. So we can now look for the determinant of the resulting sum matrix, actually a matrix of size 2 by 2, as you see. So for the first one, it will be 0, because you see the second row is a scalar multiple of the first row. As we discussed in the case of determinant, students, when a row or a column is a scalar multiple of another row or another column, there is a determinant. The determinant comes to be 0. Basically, you can also look for the determinant of this first one. 2 times minus 3 is negative 6, and again 3 times minus 2 makes negative 6. So negative 6 and negative 6 identical. So when you take the difference, it will be 0. That's why we are having 0 here, and then minus k of, again, now look, student, find the determinant of this one. So 2 times minus 1 makes minus 2, and again have minus, and when you take the product of negative 2 and negative 1, you are having positive 2. So negative 2 minus 2 is going to come, as can be shown, right? So students, negative 2 minus 2, or negative 4k is going to come. Negative 4k, I mean negative 2 times, negative 2 minus 2 makes negative 4, and negative 4 times negative k makes positive 4k, right? Yeah. 4k needs to be different from 0, because we are looking for the case where the matrix is non-singular. In the case of non-singular matrix, you see, we're rushing to make our matrix to be invertible. That is to say, when k is, you see, obtained in such a way that the matrix determinant is different from 0, we can say that the matrix has, an inverse, so that the product of the given matrix with the inverse can make an identity of size 3 by 3, as you know. So coming to this, we are having now minus 4k, because minus 2 makes minus 4. Basically, this is 4k, right? This is 4k, students. So please have that correction over here. It's going to be 4k different from 0. So no problem anyway, it doesn't have impact on the result, but you have to consider 4k. Sorry for that mistake. So k is going to be different from 0. So whatever k value you may take different from 0, the matrix is going to be non-singular matrix. I hope you have understood this in a better way.